Hello everyone. Today we will discuss about the characteristics of PN junction diode. First of all, we need to understand what are characteristics. Characteristics are actually the graphic representation of the variation of the current with the change in voltage. So here we'll just mention it. Right? So here PN junction diode, we need to study its characteristics for forward bias and reverse bias. We have discussed in the previous video what is a forward bias and what is a reverse bias condition. So we just need to draw the diagram for first the variation of current with voltage in forward bias. So first is when PN junction is in forward bias. So in forward bias we know that P of the PN junction diode is connected to the positive of the battery and N side is connected to the negative of the battery in forward bias. So this is the symbol for the PN junction diode, we know, right? And then the triangular part represents the P side and this line represents the N side. So we have to connect it to the battery. This side I am drawing to connect the voltmeter. Here also this side I am drawing to connect the voltmeter and this side to connect the battery. And here we will connect an emitter. But which emitter? I'll tell you. We have already discussed this while discussing the biasing. So here this is forward bias. So here the positive of the battery is connected to the P side. Negative of the battery is connected to the N side, right? And here in forward bias we know that the current is more. So we use milliammeter. Because the current is of the order of milliamperes, we can use a switch also. Now here a voltmeter is used to measure the potential difference, and to draw the graph we need to vary the voltage. So that's why the variable symbol is used. This arrow shows that the voltage is variable. So how this is provided? This is provided by using a potentiometer or a rheostat. Now here this side is attached to this side of voltmeter, so this will be positive, and this is negative side, so milliammeter will be negative polarity this side, plus polarity this side, and this will be minus. So this is the circuit to study the, or you can say to draw the characteristics in forward bias for a PN junction diode, right? Now in this case it is observed, first I'll draw separately and then after we'll combine the characteristics for forward and reverse bias. So if I want to plot these characteristics for forward bias only, initially what happens, this is the voltage, this is the current, right, and the current is in milliamperes, and this is in volts only. In forward bias, for low voltage, high current is observed. What happens is, if you recall the diagram of PN junction, where we studied that this is your PN, right, and when it is forward biased, what happens is that this is the direction of current. So this is the direction of the applied voltage, and this is the direction of the barrier potential. This was denoted by V naught, and this was due to this depletion layer, where we had plus 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 on this side and minus minus ions on this side. So this way, initially what happens is, when the voltage increases, it is in opposition to the barrier potential. So initially the current is very low, and then after, when this exceeds this barrier potential completely, then the current starts increasing exponentially, right? So initially the current is very low, nearly negligible, and then after it rises exponentially. So this is near about 0.6 volt for silicon. This minimum voltage at which the current starts rising exponentially, this is called threshold voltage or cut-in voltage. So I'll just mention it. The minimum voltage at which the current starts rising exponentially in forward bias for a PN junction diode is called threshold voltage or cut-in voltage. Right? Now this is, for example, for silicon, it is nearly is nearly 0.6 volt, right? Now we have to discuss the characteristics for PN junction in reverse bias. What does that mean? Here the battery will be connected, and this is for connecting voltmeter. Here ammeter will be connected, similarly here in reverse bias, P side is connected to the negative of the battery and N side is connected to the positive of the battery. That's why it is reverse biased. And then for varying the voltage, this is variable voltage, so a variable sign is there. And then we have voltmeter to measure the potential difference. And here ammeter. In reverse bias condition, the current is very low, so we use a microammeter here. We can use a key as well, and here this is minus side, so this will be minus. This is positive side of the battery, so this will be positive, this will be negative, but this side of the voltmeter will be positive, right? Then what happens is, initially a very low current flows. First I am drawing separately for reverse bias, and then after I will combine the reverse and forward bias graph. So voltage I am taking on x-axis only, so here I can say that this is minus volt. So this is reversed, the polarity is reversed. Here the current is in microamperes. So what is observed is that initially on increasing the voltage, a nearly constant low current flows, right, which increases suddenly to infinitely large value at certain voltage, which is called as reverse breakdown voltage. So I can say that this voltage is reverse breakdown voltage, right? So this is reverse saturation current, this is called as reverse right. So here a very large, after increasing the voltage to a very large value, the at reverse breakdown voltage, a very high current flows. Why it flows, I am going to tell you. What happens is, in this case of reverse bias, what is the diagram? If you recall, this is your p-n junction, this is reverse biased, so minus and plus here. Now what happens is that the applied voltage is this way, and obviously the barrier voltage is this way. Why so? because here there is an accumulation of minus ions, here there is an accumulation of plus ions. So the applied voltage is supporting the barrier voltage. So what is happening is this applied voltage is helping the movement of minority carriers along with the barrier potential. So you can say that this current is flowing due to minority carriers. As V and V naught, or you can say V applied and V naught, that is barrier potential, support the flow of minority carriers. Now as the voltage increases, what happens is that the covalent bonds break and many electron hole pairs are produced, resulting in an infinitely large current at a particular voltage, which is called as reverse breakdown voltage. So as voltage increases to very large value, the covalent bonds break resulting in many electron hole pairs, which eventually results in very high current, right? So this is breakdown voltage, reverse breakdown voltage, and this value is nearly 83 volt, nearly 83 volts. So you can say here it is 80, this is 80 volt, here it is 90 volt. So you can see easily that very high value of voltage, reverse voltage, is required for reverse breakdown, right? So this is reverse breakdown current, and there is a special device which is called as Zener diode, which works in reverse breakdown region, and most of the other devices work till the reverse saturation current region. So this was all about your PN junction in forward bias and reverse bias, and these are the characteristics which are drawn. Now I need to sum up both the graphs. Common characteristic which shows forward bias and reverse bias. So that I am drawing here, I am just combining these two. So this is for forward bias, this is for reverse bias. This current is milliampere because this is forward bias characteristic. This is reverse bias characteristic, and here the current is in micro ampere. Here this is in volts. Here also it is in volts. So we have already studied that this is the graph for forward bias region, and here it is reverse breakdown voltage. This is nearly so this point is reverse breakdown voltage. So I hope you understood this. This was all about the characteristics of PN junction diode. That's all for now. Have a nice day.